Okay, so I think we can start. Today's lecture is going to be about Feynman's theorem. So this is going to be an extension of Big's theorem. So let me recall Big Iserlis theorem. So what was the setup? The setup was that we wanted to compute some simple correlations like this: xi1, xi2, xi2k, which was by definition equal to 1 over z0 integral over rd xi1, xi2, xi2k exponential of minus 1/2 px on x dx. So this is a Gaussian, d-dimensional Gaussian, and so the Wick's theorem tells us what is that. So the theorem says that this is actually equal to a sum over all pairings belonging to P2K for now. Just use this notation. Product of xi, xj. So these are these 2-point functions. Okay, so this is over a particular pairing, which is like ij, belonging to pi. Right. So we saw that we can also write it as in another form, which is more suggestive, which is sum f gamma belonging to G1 to K. So the notation is as follows. First of all, let me start from the beginning where this 2-point function xi, xj that I'm using here actually we calculated this. This is the inverse ij. This is the ij component of the so-called propagator in this case. And P2k, right, is the set of all pairings of the set.
Professor?
One question?
Yeah, the camera isn't tracking anymore. So
Oh, the camera isn't tracking. Oh. Okay, so we'll try to fix it now.
Think.
No,
Oh, it is still in normal tracking, right?
Yeah.
It's supposed to be tracking. Can you just move?
No, it's not.
It's not.
Maybe just
I'll
go
close
to
it.
close and then yeah. Exactly. I mean, go just to tracking mode and okay, so and then yeah.
Okay.
Now it's tracking. That's kind of funny. So it's huh?
It's following me instead of you now.
Yeah, you have to come. You have to.
Yeah, and now just press normal tracking.
Now it's
Can you press normal tracking?
oh yeah, I just do that. Yeah.
That's it. I think it should be following you now.
But it doesn't.
It will if you move. I think the blue light is on.
Oh yeah.
Yeah.
Oh yeah. Okay. So far so good. Okay. Be careful. All right. So of 1 and 2k. So in this formulation, G1 2k, it's a temporary notation, G1 2k is the set of one-valent labeled graphs with k vertices. Right? So we have these two formulations, summing over pairings or summing over labeled one-valent graphs, so as we saw in the last lecture. So now today we want to generalize this to a much more setting by changing this quadratic form to a much more general function, just a smooth function in general with a quadratic form as its first component. So to set up the notation then, so today, hopefully, yeah, it's okay, can follow. So today, let's let z be equal to integral over Rd. Okay, so first of all, there is this normalization factor of h bar to the power negative d over 2, and then we have got integral over Rd, exponential of minus 1 over h bar s of x dx. Okay, where this action s of x is equal to that term as a quadratic part, okay, which I just write it as b of xx now. I discussed that we can write it in two ways, either a quadratic function or my matrix B, but they're the same thing. Okay, that's this one minus a still of x and a function, this is kind of perturbation of this. And we allow this still of x actually to take a very general form. So we just say sigma m from 0 to infinity gm bm of just write it like this is an m linear function which we compute on the diagonal xxx divided by m factorial. Okay, so we want to have a recipe to compute this integral now, this partition function. First of all, we have to say what do we mean by this, because there are a lot of issues here. I mean, it's an infinite sum, first of all, and then also this integral may or may not converge. What do we mean? But I'm going to argue that actually no matter what GMs you choose, what functions you put there, the integral has a sense, has a mathematical sense, and in that mathematical sense, we want to write an expression for it. So that's the point. Now, what these quantities are. So let me tell you what this PM, how we are going to think about PM. So this PM now from RD plus RD plus RD m times to R. It's just an m linear functional. And that's actually the Taylor coefficient of the function still. That's the empty primitive in the general sense. I mean, so Bm is equal to dm of Stella at 0. And in that way, you notice that if you neglect these GMs, this is basically Taylor expansion, formal Taylor expansion of this function Stella. That's what we're doing. So we're going to think of these BMs as tensors in this way. So these are tensors over RD, symmetric tensors over RD, M-valent symmetric tensors. That's BM. And so the sense of this quantity that it matters for us is captured here. So the definition. So let me give you a simple example. A formal Laurent series in variables in H bar. We are thinking of H bar as a formal variable now, and G, for example, one variable, is an expression of this form. So we just say sum C M N H bar to the power M, G to the power N. Right? But M and N belong to Z. It could be negative powers potentially. For both M and N can go into a negative direction, but this is okay. So M and N belonging to Z. So this is a formal Laurent series. Okay. Now the claim. Okay, so we can extend this. Similarly, can define Laurent series, formal Laurent series in variables like h, g1, g2, and then h, g1, g2 up to g infinity. That's we can define it in variables h, g1, which actually g0, g1, g2, so on up to infinity. The point is that the coefficients CMN belong to complex numbers, and there are finite quantities for each multi-index belong to C. Okay, now, so to get the sense that this guy, now, so the claim is that so the not a claim, you're not proving, you're just defining. So idea is that Z, this Z that I introduced over there, actually can give us a formal Laurent series. Gives us a formal, in this sense that I defined, formal Laurent series. To justify this idea, so let me give you an example. That Z be this quantity now, this integral, I mean, h bar to the power negative d over 2, integral RV, exponential of -1 over h bar, b of x and x, minus, so this is a one-dimensional, oh, this is over R, sorry. This is a one-dimensional integral, but I have added a quartic term to it, minus g x4 over 4 factorial, right? And then this dx. This is all in the exponent, of course. This is dx. Okay. Okay. So how can we turn this? How can we get a Laurent series from this? No matter what g is, because this integral may or may not converge depending on what g is, right? if G is negative, if G is positive, for example, this integral will diverge badly. But it doesn't matter for us. Formally, we can make sense of it in the following way. What we'll do, in fact, we just write this as equal to, we know that this is equal to h bar. Okay, so first of all, we do a change of variable. So the change of variable is we change x to root h bar x. So once you do that, then you get rid of, okay, so here is -1/2, by the way. You get rid of this h bar in front, well, because this dx will pick up this factor. So this cancels that. So then z becomes equal to something like this, integral over r, exponential of minus dxx over 2. And then we have sum. Now, okay, so this is an exponential, and then I just expand exponential into powers by using exponential, using Taylor series for exponential function, right? So what is that? That just gives me sigma, k from 0 up to infinity. And then I've got g x4 over h bar, and then over 4 factorial, the whole thing should be raised to power k. And I have to divide by k factorial. Okay? And there is dx here, right? This is just expansion of the exponential function, which is what we did. Now is the crucial step, which will give us a formal power series which is well defined. So we exchange integration and summation, which is illegal in general, and then all issues comes from this move. But it's actually good for us because it will give us something that's in each term is calculable. So if you do that, then you get sum. Then I cannot write this is equal to, but it is equal in the formal sense. Okay, so you know what I mean. Sigma k from 0 up to infinity, integral r, and then we just write it again, minus e xx over 2. This is a Gaussian, okay? And then this term here, I just keep it like that, so that's okay. Then gx4 to h bar to the power 4 factorial to the power k divided by k factorial, and then there is dx. Now, you notice each term here is well defined, right? Because this is a rapid decay function, and this is a polynomial growth for each term. So obviously, we can write it as sum c, and actually, in this case, I can just write it as c kk. There are only these terms, ckk remains, and then I've got gk h bar k. In this case, this is the one that I've got, right? And in fact, k is bigger than equal to c. So is a Laurent series. I mean, formal Laurent series. And you notice we can do this game for that general integral. So if you have infinite number of GIs, you can place this game. So you just multiply finite number of them, bring them down, exponentiate, and then each term is nice. Okay, so this is the sense that by which we want to understand the nature of these coefficients now. Any questions or comments? There is something in the chat, but this chat, okay, this chat is about the camera, so that's okay. Okay. No questions or comments? All right. So now let's go back to the general case then. Right. So let me erase this, you know. Okay, so now so let's fix some notation. Let n be equal to n0 is an infinite potentially infinite, but yeah, 0 and 1 and 2, so on, where ni belongs to n union 0. So you have a vector of non-negative integers that could be 0 or positive integers, and ni is equal to 0 for I large enough. So let's consider one of these vectors like that. So they are eventually 0, so they just don't keep going. I mean, but okay. So then we define let Gn be the set of isomorphism classes of graphs with an I-valent vertex. Okay, so for example, so this is the set Gn, set of isomorphism classes of graphs. So let me give you an example. Let's look at, for example, this simple eyeglass graph. But n2 is equal to 2, and 4 is equal to 1. And then ni equal to 0 for all I different from 2 and 4. So we have two valent vertex. This is a two valent vertex, and we have one 4 valent vertex, and we don't have any other vertex. So this gives us this sequence. Another example, theta graph. This. So here n3 is equal to 2, ni is equal to 0 for all I different from 3. We have two trivalent vertex, and there are no other vertices. So this is the theta graph. I mean, then you can construct a lot of examples. Any graph that you can imagine, you get. One thing I want you to notice is that this set Gn is finite. This is finite set. So I just say like this, since ni is equal to 0 for all I large, this implies that actually the number of vertices is going to be finite and the number of such graphs are also finite. Implies that Gn is a finite set. So this is important. Question?
Because of this final Gn being a finite set, it means that we cannot define n to be all sequences of natural numbers such that you only have finitely many non-zero ni's, because then G of n would probably be an infinite set, I guess.
I mean, G of n is defined for each n. When you
Yeah.
fix n,
Yeah, so if we define n such that ni is non-zero for only finitely many i's,
Yeah.
then G of n would be an infinite set.
no, exactly. No, that's the opposite. I don't know. I mean, I'm saying n is the set of n is a multi-index such that all of them are zero, except for finite number.
Yeah.
This implies that Gn is actually finite.
Yeah, but then we can take as big of this finite number as possible, right? So,
No, then you're changing n.
okay.
We are talking about a fixed n actually.
Yeah.
You're changing n in that case. Yeah, of course, the set of all graphs is an infinite, coming from different n's is an infinite set. That's true. But we are for each n. So let me put it. Okay, so let me put it like this. Emphasize. It implies that for each n, Gn is a bias. Oh, that's one thing. Now, another thing I want to define is the idea of contracting tensors. Okay, so contraction of tensors. Okay, so there is a map for any finite dimensional vector space V. We have this map from V tensor, I would say V star tensor n, the dual of V tensor n times V tensor n to say over complex numbers, for example, to C, where it's an evaluation map, right? For where given by t plus x is mapped to tx, where t where this t belonging to V star tensor n, which is the space of all n linear functionals on V, right? That's the notation. N linear functionals on V. So this T we can now interpret it as V cross V tensor V tensor V to C, and then if you pick an X, which is here, and X belongs to V tensor N. So this is an evaluation map, okay? Which is also called contraction. In tensor analysis, maybe in courses in GR or differential geometry, perhaps maybe you have seen it in the index notation. Here, let me write it like that. So in terms of indices, this is a bit abstract, but in terms of indices, this tensor T is a tensor that is denoted by T I1, I2, In, right? Is denoted like this. It is the tensor with the upper indices and upper index, and X is a tensor like S with the n lower index, say J1, J2, Jn. And when you contract them, is mapped to summing over all indices, but there's repeated indices, in this case, summing T, I1, I2, In, S, again, I1, I2, In, and this time for all I1, In. Okay, so this, of course, is a generalization of the trace map. So let me look at the special case. Here is an example. So if you take n equal to 1, right? So first of all, V star tensor V, we know that is isomorphic to space of matrices of V, which is, I just write it as endomorphisms of V, right? This is end of V. Or in matrix notation, in terms of basis, this is all n by n matrices, one up index, one lower index. And this map then is just like that, right? So we just say Ti tensor Sj is mapped to, I mean, in matrix, okay, so let me write it like this, is mapped to some Ti Si. But honestly, even that's not a very good notation. Better notation, of course, we just use Tij. One up, one down index. It's any tensor here is written like that. And then we are contracting over this is putting sigma Ti, which is exactly another notation for this. But it's just an evaluation map. You have in this case, you're evaluating your one form. Okay. So are there any questions? Okay, so now we have all these tensors. Okay, so let me, if there are no questions, I'll continue that. So then we have this. So we want to think of BI as maps, as I said, from RD plus RD to C. I mean, so this BI is really a tensor is a covariant tensor on RD, so to speak, for all I given. These are just partial derivative tensor of this function still that we have, right? And now, what about B inverse? B inverse also, I want to see it as a tensor belonging to RD tensor RD. I mean, so B, remember, B is a function, is a quadratic function. I mean, we have different forms of this B. It's a quadratic function of RD to C, the quadratic form. We also saw B as a D by D matrix. We can write it, this function. I mean, the connection was that B of X and Y was the inner product of Bx and Y. This was the notation. Now, once you think of it like this, you can take B inverse, and then we think of it as an element in RD tensor RD, actually, because you just write, you just sum over indices. Okay. So that's the way we want to think about these gadgets. Now, then for any graph G or gamma belonging to Gn, the Feynman amplitude F gamma. I mean, to be absolutely precise, I have to put these matrices, these tensors B and BIs here, but I don't put it, just gamma, is calculated via so-called Feynman rules. So I will speculate now. I will stipulate now via Feynman rules. So what are the Feynman rules? The rule one is that we're going to decorate this graph, gamma, decorate gamma by, first of all, we put tensors BI on each I-valent vertex. Put tensor BI on each I-valent vertex. One thing. Second of all, put tensor B inverse, the so-called propagator, on each edge. On each edge. And third, contract the all tensors according to the rule of contraction. Contract them all. Okay. So let me give you an example in how this is done in practice. Right. So imagine we have this, for example, eyeglass graph, whatever. Something like that. So at this vertex, which is 4-valent, we put the tensor B4. We put here B4. And at these two vertices, we put the tensor B2. And there are 4 edges. On each edge, we put the tensor B inverse. The propagator goes in the edge. B inverse, and then we've got B inverse. And then we have B inverse. Okay. So, and then we contract this. So by this, I mean, we just take all these tensors. So we've got B2. Okay, so we've got, yeah, B2. Tensor B2. Tensor B4 in the middle. And then tensor B inverse, B inverse, B inverse. And this you contract according to what I define, and then you get a number. You get F gamma, the Feynman amplitude of this graph for that kind of action functional gamma. So notice that we have here something that has weight 8, they match. Weight is 8. So, and here is also a weight 8, but it's a dual space so that we can pair them. Weight 8. So then you notice that for rule 3 to make sense, you must make sure that for any graph gamma belonging to GM, this is simple graph theory observation that the number of edges times 2 is equal to the sum of all vertices. Okay, need the fact that, okay, so for 3, I mean, need the fact that for any gamma belonging to Gn, twice number of edges is equal to sum of variances, all variances for vertices. And this is a simple observation. So you can do this in general, so you don't have extra. Okay. Okay. Any questions? Okay. Okay. So now I can now write down the theorem and we want to prove and start this proof. Okay, so maybe I just need zeros. So now this is the theorem that we want to prove. I mean, this we call it Feynman's theorem, but this is not the way Feynman thought about this at all. I mean, this is a finite dimensional version. I mean, for them, for these practitioners of QED, this was just, I mean, they saw all these things in terms of particles coming each other, interacting at one point and then going away. I mean, so they had a different way of thinking about it, and certainly not like this. I don't know, actually. It's a good question. If you find out who actually wrote this theorem the way I'm writing here, that would be, I would appreciate if you tell me. That's kind of nice investigation. Maybe you just go to AI or something, just ask where this thing appeared first, theorem. So the theorem is attributed to Feynman, and whether it's, yeah, indeed, should be, is that with Z defined area, I just defined it, I don't define it here. We have Z is equal to 2 pi B over 2 divided by square root of determinant of B, sum over all these indices now, n. Now we are summing over all indices, and so this is an infinite sum. Product of gi to the power ni, or Ri, but again, this time is final, sum gamma belonging to Gn, h bar to the power negative pi gamma, divided by order of the automorphism group of the graph gamma, f gamma. So this is the equality of formal power series, formal Laurent series actually, as equality of formal Laurent series in variables h bar and gi. Zero, one. And chi gamma, what is chi gamma? Where chi gamma is the Euler characteristic of the graph. Which is Euler characteristic we know is how to put it. I mean, this is number of vertices minus number of edges. Number of vertices minus number of edges. Which is also basically dimension of H0, the zeroth homology or cohomology, doesn't matter, minus dimension of H1. So it's a dimension of, I will discuss this a little bit later, dimension of H0 minus dimension of. Maybe I'll just put it up here. It doesn't matter really. Say H0 minus dimension of H1. I mean, this is quite elementary, this definition. This needs a little bit of extra work, but that's easy also. Okay. So that's what we want to prove. So, okay, so let's and then this is, of course, self-explanatory. This is counting the number of automorphisms, so symmetries of the graph. I will define it as we go on. And this is the final amplitude, and this is. One thing you should notice is that each term in the expansion is finite. So the coefficients are here is finite, this sum, because for each n here, Gn is finite. So this is a summation over a finite number of graphs. This is the variable part, and h bar is also variable. Okay. All right, so I have 2-3 minutes. Let me just tell you one thing that you have to do to prepare for the proof. One thing that we always do, which is important but easy to understand, is so proof change variable first. So this variable you just send you just say y equal to x over root h bar. I mean x belonging to RB, right? So we just switch to this. We just rescale the thing. That's important to get rid of some nuisance. This h bar. So this gives us an expressions of the form z equal to sum over Rn z n, where this Zn now is equal to integral over Rd exponential of minus b y over 2 is a quadratic form with the same coefficient. This is the part that is get gi to the power ni, and I is fixed, and then over I factorial to the power ni times ni factorial. So these combinatorial numbers are very important here. So this is I factorial to the power ni times ni factorial, right? And then times h bar to the power I over 2 minus 1 ei of yy to the power ni, and there is dy. And you see why you get these coefficients, because you remember we had this, you see, S of x was equal to 1/2 bxx minus some, you remember it was some gn over m, okay, I mean, gi over I factorial b I of xx, right? By greater than equal to 0. And then you do this change of variable here. You pick up some negative powers here. And then there is one factor of 1 over h, which is here. You're computing exponential of minus 1 over h, s of x. And that whole thing contributes this many h powers to the coefficient of the I. So this is the one. And we just use the same trick as we did. We just write it in terms of exponential functions expansion, and that's the R expansion. But here is that n is any multi-index. Okay, so n is it's a multi-index. I mean, this is not a finite. This is not a simple index. This is a multi-index. Yeah? So that's the first step. Now we're going to study each term. Now you can see what the game we are going to play. We are going to apply Wick's theorem to these terms, because this is what? Some sort of monomial. This is an I, it's what? I linear function in Y, right? This is some sort of monomial. So some polynomial actually is a monomial. The sums of monomials rather. And we are using Wick's theorem to compute these things. But then there is one trick which we use to turn pairings into graphs, because there are so many more pairings than graphs. So that's a crucial step where we switch to graphs, and that's a huge reduction in terms of, and this physicists call this Odd-Gamma symmetry factors, and they are really, of course, symmetries of the graph, but we'll see how they emerge on this thing. So this should be done in the next lecture. Okay. Are there any questions? Is that kind of clear? Or? Excellent. Yeah. I mean, you can always, of course, send me questions. I mean, that's so. Bye bye, everyone. See you in the next lecture.